So 2 plus 4 plus 3 plus 1, we have 10 roots. The number of unique roots, however, each individual one. We've got 1, 2, 3, and 4 unique roots. Which of these will create a bouncing point? So going from these here, these are all the same ones. The ones that bounce are the even ones. So at x equals 7 and at x equals 8. And then the other question, which zeros does the graph pass through at the odds? So at x equals 5, x equals -1/2. Now we can write possible equations for each of the graphs below. So possible equations. So with this, we have to look at the graph and think about what's happening at all of these points. So we have an x-intercept at these 3 points here. At x equals 4, and at x equals -2, and at x equals 3. At -2, they pass through. Okay, so here and here, they pass through. And we know that passing through means odd multiplicity. So I'll just say odd mult for multiplicity. At x equals 3, it bounces. Therefore, we have an even multiplicity. We also want to think about our end behavior, so the stuff that we did at the beginning of class. They're both going up, which means they are even. They're doing the same thing. And the right side is going towards positive infinity, which means it is even and positive. So even again, they're both doing the same thing. Positive, they're going towards positive infinity. So with that, that means it's going to have a positive leading coefficient and an even largest exponent. So f of x equals, thinking about, at 4 we have x minus 4. Passing through, it has an odd multiplicity. Well, I'm going to keep it simple and leave it as 1. So I'm not going to write anything down. At x minus 2, that should be a -4, so that should be a plus 4. At x equals -2, we have x plus 2. Again, passing through, so I have an odd multiplicity, I can just keep 1, and eventually I won't write those in there. Just keep it as a 1. Finally, we have x equals 3, so x minus 3 bounces, so it has an even multiplicity, meaning I need to have an even exponent. I'm going to put positive 2. The even and positive, so I have 2, 3, 4. Eventually I would have x to the 4th. That's my even. And a positive leading coefficient, I'm going to just not put anything there. If we had an example that was negative, I would just need to add a negative out in front of everything. So let's do this next one. Same idea here. So this is a x-intercept at x equals -3, at x equals 0, and 4. We have a bounce, pass through, and a pass through. Okay, so we've got f of x equals, thinking about again, both doing the same thing, so this is also even. The right side's going towards positive infinity, so even and positive. At x equals 3, x equals -3, we have x plus 3 with a bounce, so an even multiplicity. X minus 0, right? Okay, well that's going to be changing into something else. We've got a x-intercept at 0, so really x minus 0, hold on to that thought. We'll change that in just a second. Either way passes through, so it has an odd multiplicity. We could put a 1 or leave it as nothing there. And then x equals 4, we've got x minus 4, again another pass through, so an odd multiplicity. X minus 0, I'm going to take that and I'm going to bring that out to the front as just an x. So I have x times x plus 3 squared times x minus 4, and that's my f of x. And again, it being 1, 2, 3, 4 x values, even exponent, positive, I have positive x out front, positive 1 technically out front. And that is my possible equation for this graph. Okay, moving on to the next page with the rational zero theorem. This is the last bit of notes for today. The rational zero theorem. Sounds a little bit confusing, but once we go through examples, we end up seeing that it's actually not that bad. So if p of x is a sub n times x to the n. And when I say sub n, that's just the opposite of an exponent. It's below. A n x n. Plus a sub n minus 1 times x to the n minus 1, plus infinity in between, plus a sub 1 times x plus a sub 0. So really this is just showing that I can do this for any of these polynomials. And so it has integer coefficients, where p are all factors of the constant term a sub 0, which is really just the constant at the end of whatever thing that we're given, a sub 0. And so looking at number 1, that would be negative 6. Here it would be 8, here it would be 3, here it would be negative 12. So really it's just the factors of the final term. And q, they're going to be the factors of the leading coefficient, a sub n, the leading coefficient. So here the leading coefficient is 1, leading coefficient is 1, leading coefficient is 1. Obviously it's easier when the leading coefficient is 1, as we have that, but here leading coefficient is 2. So this is going to be a little bit different for us, number 4. P over Q is going to give us a list of all possible rational zeros. And this is important because this is going to narrow the search for rational zeros to a finite list. Because notice how I want to find rational roots, I want to do some synthetic division, but I'm not telling you what your root is, your initial root. I'm not giving you a C value to try to divide by. We have to figure that out using our P over Q. When I ask you just to find rational roots, we're going to think about the rational zero theorem, and here are the steps that we want to follow. So first step is apply the rational root theorem to find the possible rational roots. So my P over Q. Well, I'm going to break this down. Let's think about P, the possible factors of the constant at the end. So negative 6. Well, I can take negative 6 and I can say, well, that's like 1 times 6, or negative 1 times negative 6. So really, I can do plus or minus 1 and plus or minus 6, depending on which combinations I make. I think I made a mistake. So negative 1 times positive 6, or positive 1 times negative 6, not the positive and negatives. That would give you a positive 6. All right, now we want to think about our Q, our possible roots, or possible factors, of the leading coefficient of 1. Well, the only way we can get positive 1 is if we take positive 1 times positive 1, or negative 1 times negative 1, so again, plus or minus 1. This brings us to our P over Q. Well, if what I have 1 over 1, that's 1. What if I have positive 1 over negative 1? That's negative 1. So when our Q is plus or minus 1 and just plus or minus 1, our P over Q is going to end up being the same thing as P. Plus or minus 1 and plus or minus 6. And I'll show you how that changes when our leading coefficient is not plus or minus 1. So P over Q is plus or minus 1 or plus or minus 6. We want to think about our synthetic division, and I'm going to leave this for now because I'm going to show you that we have to actually guess and check to figure out what goes in this first box. We have a leading coefficient of 1, 2, negative 5, negative 6 without any gaps, which is nice. What I want to do now is think about, could my 0 be positive 1, negative 1, positive 6, or negative 6? We want to think about which one it could be. So I'm going to go through and try positive 1. I'm going to think about positive 1 as my blank spot. I have my leading coefficients. I'm just going to rewrite what I had down here. So rewrite these. And I'm going to give this a go. I'm going to see if it works. So I bring it down. I multiply. Then I add. Then I multiply. Then I add. And then I multiply. All right, so I end up having a remainder of, with a remainder of negative 8, 1 is not a 0. It's only a 0 if we have a remainder of 0. So 1 doesn't work. Well, let's try negative 1, okay? And I could try positive 6 and negative 6, but for the sake of time, I know that they're not going to work right now, so I'm going to show you the one that does work. Negative 1. Bring down the 1. Multiply, add, multiply, add, multiply, we get a remainder of 0. So with this, we have x squared plus x minus 6. But we know that negative 1 is also a 0. So we have another factor that I can bring down of x plus 1. So again, that x plus 1 here came from the fact that we now know that -1 is a 0 because it brought us a remainder of 0. What I want to do now, I've got x plus 1 as my first factor. I can factor this portion now. This factors nicely. I have x plus 3 and x minus 2. 3 and -2 multiply to -6, and they add to +1. So these here are the... So now we can think of the rational roots, our real zeros here. We've got x equals -1, x equals -3, x equals 2. Okay, number 2. And again, before we move on to 2, these are our roots. We can also call them zeros or x-intercepts. All those are the same. All right, number 2. We have f of x equals x cubed minus 2x squared minus 4x plus 8. So I'm going to think about my p, the possible factors of 8. We've got plus or minus 1 and plus or minus 8, or plus or minus 2 and plus or minus 4. So we've actually got 2 more than we had last time, or 2 more plus or minus options, so that's 4 more. Our q is the same thing, plus or minus 1. And it's nicer when the q is plus or minus 1 because that just leaves our p over q to be exactly what our p is. So plus or minus 1, I'll do this in numerical order, plus or minus 2, plus or minus 4, and plus or minus 8. For our guess and check, for the sake of time, 2 is the 0 that works here, or one of the ones that works for us here. So I'm going to go through my synthetic division, leading coefficients of 1, -2, -4, and 8. I'm going to go through, bring it down, multiply, add, multiply, add, multiply, and add. We get a remainder of 0. So from the 1, 0, 4, we have x squared plus 0x minus 4, okay? And the 2 here brings us x minus 2. All right, well, I'm going to rewrite this as x minus 2, get rid of that 0x, x squared minus 4. I want to factor x squared minus 4. That's a difference of squares. So I have x minus 2. When we have a difference of squares, our factored is x plus 2, and just the possible factors of -4, 2 and positive 2 and -2 for those ones. Because we have, let's go back through and check, x squared minus 2x plus 2x brings us 0x plus 2 times -2, we get negative. So what we really have, we have x minus 2 happening twice, an even multiplicity of x minus 2, and then we have x plus 2 happening once. So I've got x equals 2 and x equals -2 as my rational roots. All right, two more problems. We have f of x equals x cubed plus 6x squared plus 10x plus 3. Our p, our possible factors for 3, are plus or minus 1 and plus or minus 3. Our q, we have plus or minus 1, so our p over q is just plus or minus 1 and plus or minus 3. So I'm going to pick -3 as the one that's going to work. And again, I'm telling you that to save on time, you'll have to guess and check until you find the one that works. So we have 1, 6, 10, and 3 as our leading coefficients. Bring down the 1, multiply, add, multiply, add, multiply. We get that remainder of 0 that we wanted. That tells us that -3 is a root. That positive 3 is a root, that x plus 3 is a factor, so x equals -3 root. Yeah, I think I just made a mistake there on that. So x plus 3 is a factor, -3 is a root. So we have from here x squared plus 3x plus 1, that comes from here. The x squared plus 3x plus 1 comes from here, and then we have that other factor of x plus 3 coming from that -3 being a root. So we've got x plus 3 as a root. We need to think about this part right here. X squared plus 3x plus 1. That does not factor nicely. So we either have to factor or use the quadratic formula. Obviously factoring is a lot nicer and quicker for us, but sometimes we do still have to use the quadratic formula. So here factoring is not going to work. So we have to use the quadratic formula. All right, we've got negative b. So that's negative 3 plus or minus the square root of b squared, 3 squared, minus 4ac, minus 4 times 1 times 1. I'll just leave that as a 4. Divided by 2a, 2 times 1, I'll leave that as a 2. So we end up having negative 3 plus or minus the square root of 3 plus 4 is 5 over 2. So our possible x values, we've got x equals negative 3 as we knew from above when we did our guess and check and found that that brought us a 0. And then we found the roots here using the quadratic formula. We've got x equals negative 3 plus square root of 5 over 2 equals negative 3 minus the square root of 5 over 2. Those are our two options here. All right, last one, number 4. We have f of x is 2x cubed plus 3x squared minus 8x minus 12. We have our p, the possible factors of negative 12. This one's a long one. Plus or minus 1, plus or minus 12. So 1 and 12. We've got plus or minus 2 and plus or minus 6. And we've got plus or minus 3 and plus or minus 4. For our q, we have plus or minus 1 and plus or minus 2. So we've got 1 times 2 or negative 1 times negative 2. So our p over q, we have to think about, all right, 1 over 1, 12 over 1, 2 over 1, 6 over 1, 3 over 1, 4 over 1. Those all bring me the same thing that I had. So the plus or minus 1, all of the p-values, plus or minus 1, and I'll go through in order, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Now I have to think about this 2 value coming from the q. 1 over 2. So this adds to our list plus or minus 1/2. What about 12 over 2? Well, that's just plus or minus 6. We already have that. 2 over 2, that's plus or minus 1. We already have that. 6 over 2, that's plus or minus 3. Already have that. 3 over 2, that is not something we have, so plus or minus 3/2. And 4 over 2 is plus or minus 2. We already have that. So we added 2 new possibilities to our list for our zeros. In our synthetic division, for the sake of time, I'm going to show you that negative 2 is one of the ones that works. And I'm going to go through the synthetic division. So leading coefficient of 2, 3, negative 8, negative 12. Bring the term down, multiply, add, multiply, add, multiply. This shows me a 0. So I have x plus 2, again that comes from my c value up here, times 2x squared minus x minus 6. So I have to think about factoring this one here. I have to think about factoring 2x squared minus x minus 6. So again, we've got x plus 2 to start. 2x squared minus x minus 6. I have to think about my 2, and then I've got 1, so my first terms. What multiplies to negative 6, including this 2 value that we want to think about, and what adds to that negative 6 value? So let's guess and check. Let's start thinking about what we could possibly try. So we've got 2 and 1. So 2x and